The function f of n is defined for positive integers n according to the rules. F of 1 is 1, f of 2n is equal to f of n, and f of 2n plus 1 is equal to f of n squared minus 2. The value of f1 plus f2 plus f3 and so on is negative 86, negative 31, 23, and 58. So typically for a question like this, I might write out several values of f of n for values of n and see if I can find a pattern. I don't know if that's going to be the best way to go about this. Maybe another thing to do is to figure out, like, f is going to be the same value for many different values of n. In particular, for all powers of 2, it's going to be equal to 1, right? F of 1 is equal to 1. F of 2 is equal to 1 because f of 2n is equal to f of n. Okay, so if I now let n equal 2, I have f of 4 is equal to 1. Okay, so f of 2 to the k is always equal to 1. Now what about odd numbers? How would we compute f of 3? F of 3, I'll write the other rule down here. F of 2n plus 1 is equal to f of n squared minus 2. So f of 3 will be negative 1, right? Because I just let n equal 1, then I get f of 3. F of 1 is 1, so yeah, negative 1. So this tells me if I multiply this by any power of 2, so f of 6 will be equal to negative 1. F of 6 times 2, 12 is equal to negative 1. And now I'm seeing that, are all the values going to be just 1 or negative 1? I guess so. There's no way, because of this rule, if we ever apply this rule, we're going to get a 1 or a negative 1. If we take a 1 or a negative 1 and substitute it in here, we get back a negative 1. So in fact, every odd value, will be negative 1. So I'll say f of m is negative 1 if m is odd. And for some even values, I guess it's only the powers of 2. It's only the powers of 2 where it's equal to 1, right? Why don't we try and compute this for an even value which is not a power of 2? Just to see this in action. F of 14. Well, this is equal to f of 2 times 7. Well, yeah, so that's equal to f of 7, which is equal to f of 2 times 3 plus 1. So this is equal to f of 3, but f of 3 we've already found is equal to negative 1. All right, so this entire sum, f of 1 plus f of 2, all the way up to f of 100, is going to be equal to negative 100 plus the number of powers of 2 less than or equal to 100. So what are those? 1, 2, 4, 8, 16, 32, 64. 1, 2, 3, 4, 5, 6, 7. Okay, but this is not one of the answers, is it? Oh, I have to multiply this by 2, right? Because for every number that is a power of 2, not only does it not contribute to this, so we have to remove it, but we add 1. Okay, so 1, 2, 3, 4, 5, 6, 7. So the answer should be negative 100 plus 14, which is negative 86, and that is one of the answers. So I'm pretty confident in that one. Yeah, the thing that often throws me off in questions like this, I see a lot of these recursive definitions for a function f in terms of, f of 2n or f of 2n plus 1. Whenever you have some kind of definition of f like this, my first thought is always, well, how do I know that these rules end up defining f for all necessary values of n? I mean, in this case, it will, if the recursions go from 2n down to n and 2n plus 1 down to n. But if you have a more complicated way of a more complicated set of identities that the function satisfies, how do you know that, for example, you can always work out what f of 73 is or something like that? But yeah, in this case, it was nice to start working out a few values. Again, doing this also always seems somewhat inelegant to me. It always seems like there will be easier ways to do things. But then just realizing that this any new value of f we generate has to end up being negative 1. Because if you substitute a 1 or negative 1 in here, you always get negative 1. Yeah, so and then it just turned into a counting exercise, basically. If I have more to say, I'll write it down in the description. Thanks for watching.